let's talk about how we train the people who build our world. From massive bridges to life-saving tech, there's this huge gap between learning engineering theory in a classroom and actually building real-world solutions. Today, we're going to dig into how we can bridge that gap.
It's a huge question, right? But, it's something engineering educators are thinking about every single day. The future of our infrastructure, our technology, even our planet really depends on engineers who can do more than just understand the laws of physics. They need to apply them creatively to solve the problems of tomorrow.
And it all starts right here. Everything in mechanical engineering really boils down to classical mechanics. Sir Isaac Newton's laws of motion. These are abstract principles like force vectors, where you're drawing diagrams to see how different forces are pushing and pulling. This is the absolute bedrock of it all.
So how do we actually get from a force diagram on a whiteboard to, say, designing a super fuel-efficient engine or a medical device that saves lives? This is the core challenge right here, bridging that gap between the abstract principle and a tangible, working solution. Okay, so let's really dig into this problem. Academics have a name for it, the theory-practice gap, and honestly, it's a major hurdle in modern engineering education.
This visual just shows the disconnect perfectly. On the left, you've got pure theory, right? A force vector on a grid. But on the right, that's the world engineers actually live in. It's all about big data, AI, cloud computing, additive manufacturing, you name it. It is a massive leap from one to the other.
Now, to be clear, this theory stuff is absolutely essential. Don't get me wrong. Classical mechanics is like the fundamental language, the grammar of engineering. You just can't build anything without it.
But, and this is a big but pulled straight from the research, even when students totally nail the theory, they often really struggle to apply it to those messy, complicated, real-world problems. The knowledge is there, sure, but that bridge to actually doing something with it is missing.
So if the old way of doing things isn't quite cutting it, what needs to change? For a long time, the answer was just more lectures. But as we're about to see, that's just not enough anymore. This slide really lays out the shift perfectly. Think about it. The traditional model was pretty passive. You'd sit in a lecture, soak up theory, work on problems by yourself. But what we need now, for the world we live in, is totally different. We need active participation, getting your hands dirty in labs, focusing on how to apply stuff, and working together.
And I love this analogy because it just makes so much sense. It's like learning to cook, right? You can read cookbooks all day long, memorize every single recipe, but until you actually get in the kitchen, grab a knife, turn on the stove, and start messing things up, you don't really know how to cook. Engineering is exactly the same.
So this brings us to the solution. Researchers have actually put together a new blueprint for learning, a new pedagogical model designed specifically to get students into that kitchen and finally bridge that theory-practice gap. Okay, check this out. This isn't just a small tweak, it's a whole system. You can see the inputs up top, the curriculum, what industry actually needs, new tech, all that stuff. It flows through the instructors and the students to create the outputs we want at the bottom, engineers who have a deep technical grasp, who can actually solve problems, and who know how to innovate. It's a much more holistic way of looking at it.
And it all boils down to three simple but really powerful pillars. First, active learning. That means students are doing experiments, taking on design challenges. Second, real-world applications. The problems they solve are the same ones people are tackling in the industry right now. And third, feedback and reflection. Students get real, constructive feedback, and they're taught to think about their own learning process.
Okay, so what does this actually look like when the rubber meets the road? Let's dive into some really cool, concrete examples of how this new model is being used.
Yeah, the absolute key here is relevance. Instead of just grinding through problems from a textbook that's, decades old, this new approach brings cutting-edge research straight into the classroom. Students get to work on the problems that engineers are trying to crack today. Okay, for example, take the field of sustainable materials. This is super cool. Students are getting their hands on things like banana fiber composites, a natural, biodegradable alternative to synthetic stuff. Or they're testing materials made from aluminum and fly ash, which is an industrial byproduct. So they're not just learning about material science in a vacuum, they're learning how to engineer for a sustainable future.
Or how about the energy sector? Students are using real data to simulate incredibly complex tasks like geosteering. I mean, that's basically navigating a drill bit miles underground with pinpoint accuracy. They're also learning how modern reservoirs are monitored using sensor data and analytics to make everything safer and more efficient. These are some seriously complex, data-heavy challenges.
And this part is so important. They are learning to use the actual tools of the trade. They're not just reading about computer-aided design, or CAD. They're mastering it. They're running simulations with computational fluid dynamics, CFD software. They're programming robots. These are the skills they can walk into a job with on day one.
So what's the end goal here? What's the whole point of all this? It's about building a fundamentally different kind of engineer, someone who's ready for the future right out of the gate.
And the payoff is just huge. You end up with engineers who have a much deeper understanding of the core principles because they've actually seen them in action. They learn how to work in a team, how to communicate, those essential soft skills. They can solve problems with both their hands and their minds. And at the end of the day, they're just better prepared for industry, more innovative, and ready for whatever the future throws at them.
And that leaves us with one final, and I think really inspiring thought. Look, this isn't just about changing how we teach a class. This is about fundamentally upgrading our problem solvers. So if we can really re-engineer education itself, just stop and think for a second. What kind of massive, world-changing problems can the next generation of engineers solve?